Okay, I think all of you can see the screen. Okay, before we start, so there won't be any test tomorrow because I contacted Moodle team. They seems to have some issue with this particular course. Like they did not add the students, all the students probably, and they need to do some more configuration for this course. So we will have the test sometime in the next week. Few of you have requested that there is a GATE exam this weekend. Okay, so how many of you are actually writing the GATE?
Sir, I am writing, sir. Midhu Pavan Das.
And like,
Sir, I am also writing, sir. This is Chandu.
can you just raise your hand? Those who are writing
Yes.
the GATE exam. Yes. Okay, so around 8 to 10, 8 students. Okay, so when is the exam?
Aerospace
Sixth,
engineering
sir.
is on 6th. Yeah, 6th and 7th.
6th and 7th. So 6th is Saturday. Okay, so what I was thinking, maybe for your preparation, let's cancel the class for Friday. Okay, so that you get some time for your GATE preparation. I think that is okay with you.
Thank you, sir. Thank you very much, sir.
Thank you, sir.
Okay, it's do well with your GATE exam, and hope you get some good ranks as well. Like all of you are IIT or I mean IIT students, so expected that you score good ranks also. All right. So we'll not have class this Friday, so that you prepare for the GATE. Okay. And hello. Uh, Okay, and the test, about the test, let's reschedule to next week, same time if it is okay with all of you. Thursday, 8 o'clock in the evening. That was the time. It's okay?
Yes, sir.
Okay, sir.
Next week, okay? Next Thursday. And the topic remains the same, only the first chapter. So the second chapter we are currently going through. All right. Okay, so let's begin today's lecture. So we were actually dealing with governing equation for ABL. ABL means atmospheric boundary layer. So last week we saw the momentum, energy, and the mass conservation equation, and how you can actually include both the mean as well as the fluctuating part. Like you know that the atmospheric boundary layer actually consists of three components. One, there is a mean component, and there may be a waviness, sinusoidal or any other pattern, and turbulence fluctuation may be riding over it. Okay, so you can I mean, so the governing equation needs to include all these three. So we have seen that how to
Excuse me, sir.
modify. Yes.
Sir, have you shared the screen?
Oh, you can't see the screen? I see shared only.
We can see, sir.
Okay, let me reshare. Okay, is it okay now?
Yes, sir.
Okay, so we have derived like by considering the mean and fluctuating component, what are the simplified form of the governing equation by taking the Reynolds average. Okay, and we did all this mathematics, and finally we end up these will be your governing equation for the boundary layer. Okay, which includes both your mean part as well as your okay, mean acceleration basically, and you have your pressure term, which is also averaged, and your Coriolis force term as well as your frictional force, and here you have extra stress terms, okay, which are turbulent fluxes, or sometimes also called as the covariance. Okay, so these covariance terms are basically responsible for turbulent transport of the momentum and the heat. I think someone's mic is on, please mute. And you cannot ignore this fluctuation terms or the covariance terms because their magnitude is significantly large when you are in the boundary layer. Above the boundary layer, yeah, you can ignore them because the fluctuation reduces as you go high. Okay, and we have with that sort of hypothesis, we have simplified the equation for the free atmosphere, where we just consider the z direction fluctuation, and other direction x and y direction fluctuations are neglected, and you can see that the free atmosphere equation looks like this. Okay. Yes, so now the thing is, since we have only 1, 2, 3, 4, 5 governing equations, but there are more number of unknowns. Okay, so you cannot actually close this system. Okay, because the number of unknowns are more than the number of equations available to you. So there are various empirical relations which are followed to close these equations, which have both the mean and the fluctuation part. We will not go through the details for like the derivation of those empirical relation. Rather, we will just use some velocity profile which satisfies this equation. When you follow those sort of equation, it will definitely give you the solution what you can obtain by doing any numerical discretization of these equations or simulation of these equations. Okay, so we will just see the final result. We will not go to the derivation of those closure empirical relations. Okay, so before we go to those solution, let's solve this example, which is related to your turbulence. Okay, those what we have just derived, like the mean quantities and the variance, etc. So you try to solve this problem. Like it says that suppose we erect a short mast instrumented with the anemometer to measure U and W wind components. We record the instantaneous wind speed at every 6 seconds for a minute. Okay, and resulting that results to 10 pair of data. Okay, so which are mentioned here. So your objective is to find out the mean, then biased variance, or which is simply your variance, and you need to find out the standard deviation. So variance and standard deviation, they are related. I hope you know the relationship between them. And then you need to find out the covariance and the correlation coefficient between U and W. Okay, so few of these terms I have discussed in the lecture, and few I think I did not discuss. So let me give you the formulas to calculate. Okay, so for mean, you can simply all of you know like how do you calculate the mean or average. So take the terms which are obtained at different intervals. Okay, so then average of that. Then this particular second term is your biased variance. So sometimes it is called the variance. Okay, so you can calculate using this, the variance, and using this you can calculate the standard deviation. So the standard deviation is basically a square root of variance. Okay. Then the covariance, like how these data can be correlated, or how these data are varying if you compare one with the another. So that relation can be obtained using covariance term. Okay, so here you can see that so it is basically done on the fluctuation part, not on the mean part. Okay, so you just need to find out the fluctuation and get this covariance term, and then you can find out the correlation coefficient, which will be your covariance divided by your product of your standard deviation. Okay, so can you quickly try out how much you're getting for all these 5 terms?
Sir, is the variance 1.2? Variance of U.
1.2 and second one is 1.4.
Yes, yes, that is correct. Let me keep the screen share on.
So is the covariance 1.1?
Covariance 1.1. Okay, let me. Yes, 1.1. Okay. And you can calculate the other term. So basically this is the solution. Okay, so you get the mean component of the u velocity. Just need to average all this term. Okay. Then similarly, you can the mean component of the w need to average these things, which will give rise to 5 and 0 respectively. Okay, so these are having units. Okay, for your biased variance or variance, just need to first you need to find out the fluctuation part. So with your instantaneous data, subtract that from your mean. Okay, so if you do and square it, okay, then take the average. Okay, so there will be 10 terms and take the average, you will get variance for u. Similarly, you can get the variance for w. Okay, so that would be 1.2 and 1.4 respectively, and the units are also mentioned here because you can see that it will be the square of the velocity. Then it comes to your standard deviation, which is square root of your variance. So just need to take the square root, you get this. Now covariance, you need to multiply the fluctuation part and average them. Okay, so here you get negative 1.1 and the unit is meter square per second square. And you can also get then the correlation coefficient, which is minus 0.85. Okay, so what do you understand from this covariance term? Anyone know covariance and correlation term? What it indicates actually?
Sir, how the difference of the pair varies?
Okay, so what do you see in this particular question? What do you guess?
So it negatively varies. Like if one is increasing, if one fluctuation is increasing, the other one is decreasing. Something like that sort.
Yes. One is increasing, so they are oppositely varying. Okay. What about the correlation coefficient? What do you judge from that? The correlation coefficient says how close are those data in terms of variation. They are oppositely varying, but in terms of their closeness, you can see that it is nearly 1. Okay, so it's very close to 1, not far away from 1. So if it is close to 1, then the variation is very similar. Like exactly, you can say that they are varying 1-to-1 match. If it is less than that, then the correlation value will be lesser. Okay, so since it is very close to 1, so variation pattern is more or less similar. Okay, but it is in negative side. That's why you get a negative value here. Okay, so these things, those who have taken the turbulence course may have realized it in a better way, but we don't need that much of detailed information. This much of parametric understanding is sufficient. Okay, now, so before we go to those final form of the velocity equations, which is our requirement, so let's see that what is the boundary layer structure actually in the atmosphere. Okay, so that you can realize whatever velocity profile we define should match to all of this thing. Okay, all of these boundary layer structures. So there is basically various boundary layer structures. Like as you go high in the atmosphere, the boundary layer actually evolves. Okay, so it is not like a unique way of evolution. There are various sublayers. Okay, so here I have mentioned different sublayers, and why these sublayers appears because of your diurnal cycle. Okay, so diurnal cycle is basically day and night cycle, in other words you can say. So since you know that in the daytime you have the solar radiation, which is which is mostly felt and absorbed by the Earth surface, whereas in the night time you don't get that much of direct radiation. Maybe some indirect radiation will be there because of the atmosphere, and mostly in the night time you have cold condition compared to the daytime. Okay, and this also varies when you are talking about in the summer and when you're talking about in the winter or different seasons. Also this temperature distribution varies. So you can see here there are two plots, one showing you a straight line, the other one is showing that there is a fluctuation in the temperature. Okay, so can you say which one is in the boundary layer, which is away from the boundary layer, by just looking into this plot? Like already we know that the temperature is fluctuating in the boundary layer, so that's why this will be inside the boundary layer. Okay, and another thing is here I have mentioned the pressure terms. Okay, you can see that the line which is fluctuating, the pressure for that corresponds to 97.5. Okay, so the other line is the pressure corresponds to 85. Okay, so in this, since you go high in the atmosphere, the pressure reduces. So definitely this is something above in the atmosphere, and this is inside the boundary layer. Okay, so you can see that the temperature fluctuation inside the boundary layer is not, or there is temperature fluctuation inside the boundary layer, but in the free atmosphere, okay, above the boundary layer, you basically see a steady pattern. Okay, there is no change in the temperature on a diurnal basis. Okay, so you see that here there are different dates mentioned. Okay, 7, 8, 9, 10 June, and this data is from Oklahoma. So you see that during noon it attains peak, and then it follows this sort of variation. Okay, so when you have solar radiation, temperature increases, so you get a higher temperature there, and gradually it reduces as sun sets. Okay, so this diurnal cycle basically affects your boundary layer development and the growth of different sublayers. So there are different sublayers you can see here. One is your surface layer. Then there are in the surface layer there are subclassification, which I'm not discussing here. Like you should know there are like inter or molecular sublayer or inertial layer. Okay, so those are part of the surface layer, which you will not see in the detail. And the above surface layer you have convective mixed layer, or sometimes it is called mixed layer. Then when you the other layers are like stable boundary layer, and you can see the residual layer. Yeah? Above that you have free atmosphere, and between free atmosphere and this boundary layer you have a inversion zone. Okay, so this inversion zone is sometimes called capping inversion. Okay, so these are the sublayers which broadly categorize your boundary layer. Okay, now let's see what are the layers we see during the daytime and during the night. Okay, so during the daytime, what you can see here, let's start from the noon and you go to sunset. So during that time you get the most amount of sunlight. So you can see that the boundary layer basically it contains surface layer and your convective mist layer. Okay, so these are the two main components that you see during the noon to sunset. Okay, so after sunset till sunrise, okay, after sunset till sunrise, you see surface layer, then stable boundary layer and residue layer. Okay, so this is during the night time. Okay, when there is no sun. Then once the sun rises and up to moon, so up to noon, then you get surface layer as well as your development of the convective mist layer, or which is also called the mixed layer. Okay, so this is how your boundary layer actually evolves in a diurnal manner. Okay.
Sir, can you please explain the like features of these other layers?
Yes, we will see the features of all the layers. Okay, so now let's see the surface layer first. So surface layer, like both in the day and night time, they can be generalized in this way. So surface layer, it is 1/10 of the atmospheric boundary layer. Okay, so it is if you think about its height in terms of boundary layer thickness, it is 1/10 of the atmospheric boundary layer. Okay, so it is very close to the Earth's surface, and in this layer, basically, you see the surface properties like heat fluxes, moisture, and air mass. Those are predominantly seen. Okay, and most of the buildings, what you see, the normal size buildings are inside this surface layers. Okay, and what else is mentioned here? In this layer, basically Earth rotation is negligible because you can see that the velocity values very close to Earth's surface is 0. Right? It is the velocity of the Earth's surface which is 0. So that's why you can neglect the rotation effect, like the Coriolis forces and even centrifugal force effects can be neglected. Okay. So in this surface layer, basically small scale turbulence are seen. If you go further down, like I said, surface layer can be further divided into two categories, like molecular layer and inertial layer. So in the molecular layer, you see the viscous diffusion. Okay, so where your small scale turbulence diffuse into heat. Okay, so viscous diffusion, you can see that, and slightly above where you see inertial layer, there you can see some small scale turbulent eddies. Okay, so generally, like so in the surface layer, the small scale turbulence are observed. Okay, and they are formed because of several regions, like maybe due to the trees, woods, the forest lands, or the buildings. When there are flow around these regions or structures, you start to see some form of circulation developing, and those can be very small scale. Okay, so those fluctuations can be very small scale. So those are small scale turbulence. Okay. So in this region, basically you can see that this can act as a turbulence production, and the amount of surface stresses is actually realized. The largest amount of surface stress you can see in this layer, because if you remember the boundary layer profile, the closer you are to the Earth's surface, or the closer you are to the solid surface, the velocity gradient is larger. Okay, so since we are talking about very close to the Earth's surface, the amount of turbulence stresses realized in this particular layer will be the highest. So in other words, you can say that the wind experience a lot amount of drag. Okay. For its motion in this particular layer, because the turbulence stresses are basically what it is some form of drag which the wind is experiencing. Okay, so since the velocity gradient is largest in this region, so the amount of surface stresses is also higher. Okay, and that defines your shape of the wind profile later on. Okay, let's say for example in certain surface layer your surface roughness is largest. Like for example, if you have a grassland or a jungle or urban buildings. Okay, so for all these different regions, you will get different surface roughness, and that will again define your wind profile. Okay, so and generally a logarithmic profile can be very well provided for this particular region. Like we said, we discussed earlier, you need to have some empirical profile that follows your boundary layer governing equation. So logarithmic profile is one of such profile. So logarithmic profile is very well matches the velocity values in this region. Okay, so we will see logarithmic profile. What is the equation for that? All right, subsequently. So this is about the surface layer. Any question?
Sir, there it is written that Earth's rotation is negligible.
Yes.
Can
Earth rotation is negligible because you can see that the velocity values in this region is very small. Since you are very close to the Earth's surface, the velocity will be equal to your Earth's velocity. Okay, on a non-rotating frame, you can assume that is 0. Okay, so that's since the velocity is very close to Earth's surface, so it is quite small. So Earth's rotation effects can be neglected. Okay, so that is what it means here. All those Coriolis effects, centrifugal force, those can be neglected in your governing equation. All right. Okay, so then next go to the next layer, which is convective mixed layer, or also called as mixed layer. So in this case, this layer is developed because of two regions in general. One is because of your solar radiation, which is received during the daytime. Okay, and the second one is because of your wind shear. Okay, so in this region, when you go higher than the surface layer, your wind velocity is comparatively larger. And if you see in the free atmosphere and see the velocity values in the convective mixed layer, the velocity gradient is also still there. And because of the velocity gradient, there will be formation of some form of instabilities that Kelvin-Helmholtz instabilities or KH instabilities. So that will also lead to formation of some form of circulation. Okay, so that is one region of your convective or circulation formation, and the other region is the thermal effect itself. When you heat up the surface due to the solar radiation, the air get heated up as well as it starts to move high because of its density reduces as you hit the air. It moves high, and gradually it cools down after a certain height and the cloud formation happens. So there will be a cycle here. You can see here you are heating up the air, which is very close to the surface, and it goes high and gets cool, and it again comes back. Okay, so because of this cycle, there will be also formation of another circulation. Okay, so two main regions. One is this thermal effect, which is causing a convective type of flow or the circulation, and the other region is your shear, due to the shear of free stream velocity as well as the boundary layer. Since there is a velocity gradient, because of that there will be also formation of circulation due to the instabilities. Okay, so you can see that these two regions or these two effects combinedly form a convective mixing. Okay, in the boundary layer. So that is what mentioned here. So most amount of
can you please explain the first effect again before the cloud formation?
Okay, the first effect is that is basically your velocity gradient effect. So you can see that in the free atmosphere, as you know, the velocity values is larger than the boundary layer velocities, right? Because in the boundary layer you get viscous effects. So now, since there is a velocity gradient here the velocity are larger, here the velocity are small, so there is a velocity gradient. Because of this velocity gradient, you start to see different instabilities. One of these instabilities is called KH instability, Kelvin-Helmholtz instability. So due to which the free atmosphere, the air in the free atmosphere, they starts to curl. Okay, so you might have seen when you see in very clear sky, some clouds they look like curled. Okay, Kelvin-Helmholtz instabilities. I think you might have studied this in your preliminary courses for introduction to aerodynamics. So those KH instabilities that causes some form of circulation. Okay, and there is another circulation which is generated because of this thermal effect. Okay, so you are heating up the air, and the air goes up because of its density reduces, then it comes down as it gets cool. Okay, so that cycle is there. So these two cycles combinedly form the convective mixed layer. All right. So in the convective mixed layer, you basically have a lot of movement of the air, and the turbulent scale in this case is quite large compared to your surface layer. Okay, so in the surface layer, as I have said, you can only get small scale turbulences, but that means your velocity and length scale, I mean your temporal scales are small in the surface layer, but in your convective mixed layer, you have larger eddies. Okay, so they contributes a large mixing, okay, or variation in the temperature. So here they are mentioned, as well as you can see in the convective mixed layer, since there are a lot of large scale eddies. So you also see if there is some exhaust from the chimney, so they may form different dissipation, okay, or dispersion pattern. We will see this subsequently. So depending on what kind of eddy structures you see in the convective mixed layer, based on that you will start to see different type of pattern of this exhaust from the chimney. Okay. Yeah, so that is what it is mentioned. Okay, and mixed layer, it grows by entraining the air from the free atmosphere. So the basically the growth happens because of the entrainment of the air above it. Okay, and again you can see that during different time of the year, like during different seasons, maybe in the summertime you will get a larger convective mixed layer because the amount of heat received and the dissipation of the heat is larger. So because of that, the growth of the convective mixed layer will be larger in the summertime, and in the winter time it will be small. Again, the similar variation you can also realize during the daytime. That means during the noon to sunset, and during the early morning, the length will be also smaller. Okay, so that is what you should, and so you can realize why it is higher at certain part of the day and why it is smaller. Then we go to the next layer, which is your stable layer. So stable layer, it is seen during the sunset time, like after sunset in the evening and the night time, you see the stable boundary layer. So in this region, what happens? So it is just above your surface layer, and it can vary up to like 100 meters to 500 meter deep, depending on the surface roughness. Okay. And also which time of the year you are discussing, like whether it is in summer season or the winter season. So in this region, what happens? You basically see stabilization of this convective circulation. Okay, so during the night time, since the thermal effects are reduced, so you don't get those thermal plumes which are coming from the Earth's surface. So those thermal plumes are not visible. So some part of the atmospheric boundary layer, they are stabilized. Okay, so the motion is I will say it's not so much of turbulent. So it is significantly less turbulent compared to your convective mixed layer, but slightly higher than your surface layer. Okay, and this happens because you are actually receiving less amount of heat during the night time. So basically there is no sun, so the surface radiation is significantly reduced. Okay, so due to that, the part of the boundary layer is stabilized. It's basically a velocity profile is stabilized. So you see a stable boundary layer. Okay, and generally you see forced dew fog in this particular region of the atmospheric boundary layer. Okay, so above this stable boundary layer, you can see that there is something called residue layer. Okay, so residue layer is above the stable boundary layer, and it's a part of, if you see how it is actually formed, it's a remnants or the part of your previous day convective mixed layer. So a part of the convective mixed layer is stabilized, like this amount of sun received or amount of solar radiation received is reduced. So that's why part of the boundary layer is stabilized, and you can see that the reason for this stabilization is also because air in this region is dense compared to the air in this region. Okay, so so the movement of the air can be reduced because air is heavier in general. Okay. However, in this region, since the air is dense, still dense, so it can have some circulation in it, but that circulation is just coming from the previous day convection. I mean that when the sun was there, whatever effect was there, it is just carried to the evening time or in the night time. So this layer is actually part of the previous day convective mixed layer. So that's why it is called a residue layer. Is a residue of a convective mixed layer. So all the effects will be seen, but in a reduced scale. Okay, so that is what you need to understand from this. And I think the last one is your free atmosphere. Like you know, in the free atmosphere there is I mean, there is not much of temperature variation. Like previously I have shown, the temperature more or less stays same throughout the all day and night time, since there is not much of solar absorption of the solar radiation. Okay, so the temperature stays the same during a season. During the summer time and the winter time, there will be some variation with respect to that, but otherwise it is same. Then and geostropic wind is seen in that region, like already we have seen. Here in this case, you have force balance between different forces, pressure, friction, Coriolis force. All those force effects will be seen inside the boundary layer, but outside you don't see that. Okay, so that is the free atmosphere. Between this boundary layer and free atmosphere, there is a capping inversion zone. So this inversion zone basically indicates there is no clear demarcation between the boundary layer and the free atmosphere. So there can be a region which you normally call as inversion region. Like you can either say this is a free atmosphere part or it's a boundary layer part. So that's why it is called a capping inversion region, since in this particular region you cannot distinguish whether it is a part of boundary layer or part of free atmosphere. Okay, so you may get some velocity gradient there. In some cases, the velocity gradient is so small that you can consider this as to be free atmosphere also. Okay, so I think that is about the atmospheric boundary layer structure. And then we also need to discuss few terminologies which we will be using in the definition of the velocity profile or empirical velocity profile for the boundary layer equation. So these are few terminologies. One of these, the first one is surface roughness parameter, which is normally denoted as Z0. Okay, so what is this surface roughness parameter? It is the measure of the retarding effect comparatively uniform roughness on the wind speed near the ground. So it is a measure of the retarding effect to the wind speed near the ground. Okay, so if higher the surface roughness effect, higher retardation the wind will experience. Okay, so in this manner you can realize. So how much retardation is the wind is experiencing, that you can define using this parameter, and there are different values are mentioned here. For Shand, you can see that the surface roughness parameter is quite small, and in this case the wind experiences smaller drag compared to the other values. As you go high, like snow surface, then grasses, then also you have pine forest, then you have densely built up suburbs and larger cities. Okay, so you can see that gradually the surface roughness parameter values are increasing. Okay, starting from 0.01, it can go up to 300 centimeter. Okay, so in this case, you can see that the wind is experiencing a significantly large uh, surface roughness or drag. Okay, so how do you define this particular parameter? It is not like a particular region you have a tall building, so you can say that the surface roughness parameter is that much. No, it is not like that. You have to have this particular terrain pattern should be at least prolonging till a distance of several kilometers, maybe 5, 6 or 10 kilometers. So if you see that such surface roughness or such buildup is going on, like if a sand base is there for hundreds of, sorry, not hundreds, maybe 5 or 10 kilometers, or snow surface is there for 5 or 10 kilometers, then you can assume that for that particular region, the surface roughness parameter will be Z0, and that will have this much of value. If it is suddenly varying, like you have a larger city build up for a small distance, then you have suburbs, and if there is a mixed kind of pattern, then you need to take an average of it. Okay, so that average value will be also given to you during your exam question or problem statement. So that average can be obtained. Okay, I think it is going to be 12. So we will discuss the other parameters tomorrow. All right. Any question?
Yes, sir. Sir, what would be the effect of that ozone layer in the boundary layer? That
ozone layer, it's, you can say that is near to your inversion region. Okay, so basically you get some form of absorption, and so that helps to probably improve your convective mixing in terms of, if you want to find out what will be effects in the boundary layer, it will try to help to improve your convective mixing layer. If your ozone layer depletion is if your ozone layer is depleted, then maybe the convective mixing is not so good. Okay, a particular region in the Earth's surface, you can see that how the convective mixing can change. All right.
that turbulent eddies will be that
Yes.
minimized.
Minimized, yes.
That scale will be low, sir. That is.
Yes, it will affect your convective mixing. So the circulation scales will be different. If you have in a region, if you have higher absorption, if you have proper ozone layer, then you can expect that the turbulent eddies will be larger. But if you have not significant absorption due to the ozone layer depletion, then the turbulent scales will be smaller. Okay.
Yes, sir.
Okay. Let me take the attendance.